Hello students, welcome to today's class on Theory of Machines. In the last class, we started the discussion on band brakes. So we saw its construction details and working to start with and learnt about the forces and tensions involved in it. We then revised the concepts of tensions through belt and pulley and further derived the equation of ratio of tensions which we will use in the analysis of band brake today. So moving ahead with the topic, let's see this line diagram of simple band brake. As you can see, it consists of a drum and a belt or flexible steel band lined with friction material, which embraces a part of the rotating drum. One end of the band is attached to the fulcrum, that is point O of the lever, while the other end is attached to the lever at the distance A from the fulcrum. The force P is applied at the free end of the lever, which turns about the fulcrum point. This tightens the band on the drum and hence the brakes are applied. The braking force is provided by the friction between the band and the drum. Now let us try to find out the force P, that is, let us derive the equation of P to be applied at the end of the lever for clockwise and counterclockwise rotation of the drum. T1 is the tension on the tight side, T2 is the tension on the slack side, theta is the angle of wrap or contact of the band on the drum, mu is the brake lining friction coefficient, R is the radius of the drum, and P is the force applied at the end of the lever. Now, limiting ratio of tensions is given by T1 by T2 is equal to e to the power of mu theta as discussed earlier. And the braking torque on the drum is given by TB is equal to T1 minus T2 into R. Now let's consider the first case and find out the value of P for clockwise rotation of the drum. For clockwise rotation of the drum as shown in figure, the end of the band connected to the fulcrum O will be the slack side with tension T2 and the end of the band attached to A will be tight side with tension T1. Now let's take moment about the fulcrum point O. So force P will rotate the lever in the anti-clockwise direction about the fulcrum, so the moment will be positive with magnitude P multiplied by the perpendicular distance of the line of action of the force P from the fulcrum, that is point O, which is nothing but the distance L as shown here. Further, the tension T1 will rotate the lever in the clockwise direction about the fulcrum O, so the moment will be negative and the magnitude will be T1 multiplied by the perpendicular distance of line of action of T1 from the fulcrum point O, which is A as seen in figure. As tension T2 is passing through the fulcrum point, so its moment about O will be 0 as the distance of T2 from O is 0. So the moment equation will be PL minus T1A is equal to 0. PL is the anti-clockwise positive moment and T1A is the clockwise negative moment. So this will give us P as equal to T1 into A by L. So this is how you can calculate the force applied in case of clockwise rotation of the drum. Move to the second case, that is find out the value of P for the anti-clockwise rotation of the drum. As shown in figure, as the drum is rotating in the counterclockwise direction, the end of the band connected to the fulcrum O will be the tight side with tension T1 and the end of the band attached to A will be the slack side with tension T2. Now as earlier, let's take the moments of various forces in free body diagram of the lever about the fulcrum O. Now as you can see from the figure, the force P will again have a positive moment as seen earlier and its magnitude will also be the same as earlier, that is P1 into L, where L is the length of the lever or the perpendicular distance of the line of action of force P from the fulcrum. And now tension T2 as shown in figure tends to rotate the lever in the clockwise direction, so the moment will be negative with magnitude T2 into A, where A is the distance between A and O or the distance between the line of action of tension T2 from the fulcrum. As the force T1 is passing through the fulcrum point, so its moment will be 0 as discussed in earlier case also. So we can write the moment equation as PL minus T2A is equal to 0. PL is the positive anti-clockwise moment and T2 is the negative clockwise moment. So this will give us P as T2A upon L. So this is how you can find out the value of applied force in both the clockwise and the anti-clockwise rotation of the drum. And this is all about the analysis of the simple band brake. I hope you have understood the concept and will now be able to solve the numerical problems based on simple band brake. So now let's take up a numerical problem. Problem statement is as follows. The figure shows a simple band brake which is applied to a shaft carrying flywheel, that is rotating drum of mass 300 kg and of radius of gyration 350 mm. The flywheel rotates at 200 rpm. The brake drum diameter is 260 mm and the coefficient of friction is 0.2. The angle of lap of the band on the drum is 210 degrees. If the braking torque is 39 Newton meter, find the force applied at the lever end, the number of turns of the flywheel before it comes to rest, and the time taken by a flywheel to come to rest. So now let's understand the figure. For a simple band brake, one end of the band should be connected to the fulcrum, whereas the other end of the band may be connected to the lever either towards the same side in which the force P is acting or towards the opposite side in which P is acting. Here, other end is in the opposite direction. Therefore, the applied force will be in the downward direction as shown in the figure. This is a point to be noted. Now let's start solving the problem and see what's given. Mass M is 300 kg, radius of gyration K is equal to 350 mm, that is 0.35 meter, number of revolutions is 200 rpm, diameter of drum 260 mm, so the radius will be 130 mm, that is 0.13 meter, mu is 0.2, theta angle of wrap is 210, which will be equal to 3.66 radians, and braking torque is 39 Newton meter. Now let's find out the force applied at the lever end. As the braking torque is given by Tb is equal to T1 minus T2 into R. So by putting the value of Tb, we have T1 minus T2 as 300 Newton. This is equation number 1. Moving ahead, now let us find out the ratio of tensions T1 upon T2 is equal to e to the power of mu theta. Writing in terms of log, we have 2.3 log T1 upon T2 is equal to mu theta. Mu is equal to 0.2 and theta we have calculated as 3.66. So this gives us 2.33 log T1 upon T2 as 0.7322. And therefore log T1 upon T2 is equal to 0.3188. And this gives us T1 upon T2 is equal to 2.08 and therefore T1 is equal to 2.08 T2. This is our equation number 2. Now substituting the value of T1 in equation 1, we get 2.08 T2 minus T2 is equal to 300. This gives us T2 is equal to 277.77 newtons. Further, substituting the value of T2 in equation 2, we get T1 is equal to 2.08 multiplied by 277.77. That is, T1 will be equal to 577.76 Newton. Having calculated T1 and T2, let's take the moments of the forces about the fulcrum point O. So let's see the diagram once again. So this is the diagram. Force P will be moving the lever in the clockwise direction about the fulcrum point. So the moment will be negative and the magnitude will be P into the distance between the force P and the fulcrum point, that is 390 millimeter. So P into 390. T1 is passing through the fulcrum point, so its moment will be 0, and T2 will be rotating the lever in the anti-clockwise direction about the fulcrum point, so the moment will be positive and the magnitude will be T2 into distance AO, that is 130 millimeter. So we can write the moment equation as P into 390 is equal to T2 into 130. Putting the value of T2, we get P is equal to 92.59 Newton. So this is the value of force applied on the lever. Moving ahead, we have to find out the number of turns of the flywheel before it comes to rest. So let's take N as the number of turns of the flywheel before it comes to rest. The kinetic energy of rotation of the flywheel is used to overcome the work done due to braking torque Tb before the flywheel comes to rest. So let's see the kinetic energy of rotation. Now the kinetic energy of rotation of flywheel is given by half I into omega square. This is multiplication sign. Now putting I moment of inertia as m into k square, where m is the mass and k is the radius of gyration. Further putting the value of omega as 2 pi n divided by 60. We have this equation. Now putting the values of various parameters, we get half m is 300 kg, k is 0.35 and n is 200 rpm. So we get the value of kinetic energy of rotation of the flywheel as 8060.17 Newton meter. Further, the work done by the braking torque in n number of turns of the flywheel is given by Tb into angular displacement in n turns. So work done is equal to torque into displacement. This will be equal to Tv into 2 pi into n, where 2 pi is the angular displacement in one turn. So angular displacement in n turns will be 2 pi into n. Putting the value of Tb, we have work done by braking torque as 39 into 2 pi n. Now, as we have discussed earlier, the kinetic energy of rotation will be equal to the work done by the braking torque. So equating these two, we have 8060.17 is equal to 39 into 2 pi n. This will give us n as 32.89. Therefore, the number of turns of flywheel before it comes to rest is 32.89. Further, let us find out the time taken by the flywheel to come to rest after applying the brake. Now n is given as 200 rpm. This means that 200 revolutions are made in 1 minute, and the flywheel comes to rest after applying the brake in 32.89 revolutions. So let us find out the time for 32.89 revolution. Time for 200 revolutions is 1 minute. So time for 1 revolution will be 1 by 200 minute. Therefore, the time for 32.89 revolution will be 1 by 200 into 32.89, which is equal to 0.16445 minute. Converting this to seconds, the time taken by the flywheel to come to rest after applying the brake is 9.867 seconds. So this is how you solve this problem. I hope now you will be able to solve such type of problems based on simple band brake. So this is all for today's lecture. In today's lecture, we discussed the analysis of band brake and derived the equation of applied force. We then solved a numerical based on the simple band brake. In the next lecture, we will discuss differential band brake. I hope you will practice solving more such problems on simple band brake, and in case of any doubt, please feel free to contact me. Thank you.